apply this virtual displacement to this state when it's already in equilibrium. In equilibrium, it comes until here, but this is, of course, I exaggerate. This is very highly exaggerated. This displacement is normally small, but to show that it will deform, it will displace u and v come to here. Then delta u's mean we give virtual displacement in x direction by this virtual displacement delta u. Okay, we keep, then when we move here, v is not moving. Okay, we don't give virtual displacement in y direction, only in x direction first. So in this case, we have to evaluate what is the delta external. Delta external here is just equal to F u delta u. Okay. At this point, you have the load, you have the force Fu acting, and it is this point move in the direction of action of Fu by delta u. So the work done is this. So next, to get internal work done. To get internal work done. Internal work done, we have to look at all this member here. All this member here, when it is acted by this loading, you have internal forces. Internal forces T1, T2, T3, T4, T5 all developed in the member. Okay, in the member. And each of the member will become longer. Each of the member will become longer. So, and if when it comes to this state, then you apply this delta u virtual displacement. So each of the member will become also longer by some virtual elongations. So each of the member will be also extended by virtual elongations. And by definition of the work done by internal force, then we are going to get the internal force done, the work done by the internal force is equal to negative T I delta EI. Okay. And this one, you must do the summation. How many members there? I is equal to 1 until 5. Okay. So this is the work done by the internal force. The internal force is the member forces. And because of this delta U, then each of the member will further elongate by these virtual elongations. By virtual elongations. So now, if you apply PVD, then this one plus this one, we make it equal to 0. Okay. But now you have delta EI and delta U. Okay. Delta EI and delta U, and they must be related. They must be related. So that all these members are still stay together. And how do we relate them? Remember in our class on theory of elasticity, we have a compatibility relations. We have a compatibility relations. So E is equal to U cos theta I plus V sine theta I. The compatibility conditions that we derive. Yeah, to make sure that all this member, when you come here, it stay together. So there is a relationship between each of the elongations and the U and V. So we make use of this. So this one also is a kind of condition that we must satisfy so that the virtual displacement is kinematically admissible, which means the members still stay together. They cannot separate. If they satisfy, then the members stay together. So then here, this one you can make it as delta EI equal to delta U cos theta I plus delta V. This is virtual displacement sine theta I. Okay. But here, when we first start, this one is 0. So we have only, so delta EI equal to delta U cos theta I. Because at the first stage, we give virtual displacement only in U directions, delta V we maintain 0. So this one is 0. So we substitute this into there. Okay. So finally you get delta work internal equal to minus summation I is equal to 1 until 5 here. Ti delta U cos theta I. So now we have delta U on this side, also delta U on this side. Now we combine this, and this into this. Okay. This one and this one, you plus this one, and then make it equal to 0. Okay. Let me write it down here. Okay. So you have F U delta U plus negative of this I is equal to 1 until 5. Ti delta U cos theta I, this one must be equal to 0. So you take it U minus, right? Yep. So when we come here, this is virtual displacement. So this is any value that we can apply. So for this multiplied equal to 0, this must be equal to 0. So if this is equal to 0, then finally we get the equilibrium equation. Okay. You can get the equilibrium equation, which is so if this is equal to 0, we make this multiplied with this must be equal to 0. This is virtual displacement. It can be any value. Then this must be 0. If this is 0, then finally we get right here. Two. So you get the equilibrium equations in x directions by using principle of virtual displacement. We don't go back, we don't make use of the classical definition, but we use PVD, we get the equilibrium equations. Okay. So this equilibrium equation applies to whether the material property is elastic or non-linear elastic or any kind of material properties, because we don't consider the material properties here. So in the same way, if you repeat this process, next you apply virtual displacement in V directions. You repeat the process. Okay. First we apply in U directions, then next you apply in V directions. You give this virtual displacement delta V. Then you get the external virtual work, which is FV delta V equal to internal virtual work, summation of Ti, okay, sine, okay, summation of Ti delta EI, and make use of these compatibility relations. Then finally, you are going to get the second set of equations, okay? You're going to get the second set of equations, which is FV equal to summation I is equal to 1 to 5 Ti sine theta I. So So by using principle of virtual displacement, we get this. By using this. So that is a proof that we can use principle of virtual displacement to derive equilibrium equations. We can also, the one that we have done before in theory of elasticity is using equilibrium of internal force and external force. But here we use principle of virtual displacement. So this example, you can go through in more detail in the notes that I share with you. Okay, and also there are some explanation there. What do you mean by this kinematically admissible virtual displacement? It explained there in more detail. Okay. So in the same way, if I give you another example, if I give you, for example, now this is a truss, I give you now, if I give you this problem, okay, so this is just a spring problem, and there are two springs connected in series. Okay, one spring 1 with K1, and then spring 2, material constant is K2. Then, if I ask you to get the equilibrium equations for this using principle of virtual displacement, okay, we can also apply to problem like this. Of course, we can also solve this using the normal definition of equilibrium and try to get the equilibrium equations. We can also apply principle of virtual displacement to get the equilibrium equation for this problem. Okay?